In the branching process, we start from a single individual in generation 0, which produces some number of descendants according to some known probability distribution. And then in generation 1, each individual independently produces its descendants according to the same probability distribution as the previous generation. So this generation change goes and on and on. So the time variable in the branching process is the generation. And the state variable is the number of individuals in each generation. So here's the scenario. In generation n, there are xn individuals, and in generation 0, there is a single individual, almost surely. And in generation n, each individual independently produces j descendants with a known probability pj that comprise the next generation. So our questions are the following. What are the mean and variance of the population size in each generation? And what is the probability of extinction? In order to calculate the mean and the variance of the population size, we use the method of probability generating function, or generating function in short. Here we review some general properties of the generating function. So for the moment, forget about the branching process and consider some random variable x from a sample space omega to the set of natural numbers, including 0. And we want to calculate the mean and the variance of this random variable. And we define the generating function g of s as this expectation value of s to the power of x, which is just this. So this is the probability that the random variable x takes the value of n times s to the power of n, and sum over n starting from 0 to infinity. And if we differentiate this function once with respect to s, then we get this. So if we set s to 1, we have this, because 1 to the power of x minus 1 is just 1. So we have this, which is the expectation value of x, which is the mean, mu. And if we differentiate this function again, so we get the second derivative as this. So x times x minus 1 times s to the power of x minus 2. And if we decompose this into this sum, we have x squared here and x here. So if we substitute s with 1, we have expectation value of x squared minus the expectation value of x. So this expectation value of x squared is the variance plus mean squared. So in terms of the second derivative of the generating function, we can express the variance as this and mean as this. So from the generating function, we can calculate the mean and the variance. Now let's go back to the branching process. We first consider the generating function of pj. So pj is the probability for one individual to produce j descendants. Okay, so its generating function is, by definition, is this. So j runs from 0 to infinity. In particular, if we replace s with 1, we have g of 1 is equal to 1, because it's just the sum of all possible probabilities. Now, let gn of s be the generating function for the random variable xn. xn is the population size of generation n. So by definition, it's this. Now, since x0 is 1 almost surely, so this is the initial condition. In generation 0, there is only one individual, so that's 1. Therefore, the probability that the population size of generation 1, that is x1, is equal to j is given by pj, which is just this, okay? Because in generation 0, there's only one individual. So all the individuals in generation 1 are produced by a single individual. Therefore, this probability is just pj. Therefore, the generating function for generation 1 is this, which is equal to g of s, which we have found here. Okay. By the way, the generating function for generation 0 is just s. So finding this is a quite easy exercise. So now we know the generating function for generation 1. Now we want to find the generating function for generation n, for any n. For generation 1, it was easy because we knew this probability distribution is given. But for generation n, we don't know this probability distribution. So what shall we do? To find this probability distribution, we derive a recurrence formula for the generating function. First, suppose we know this generating function for generation n-1. Okay, of course we don't know it yet, but just assume we know it already. Then, by the partition theorem, this probability, so xn equal to m, can be decomposed into this way. So this is the conditional probability that the population size of generation n is equal to m, given that the population size of the previous generation, n-1, is equal to r, times the probability that the population size of the previous generation is r. And we sum over all possible values for r, from 0 to infinity. Next, let's say if each of the xn-1 individuals in the previous generation produce yk descendants. So k varies from 1 to 3 up to x minus n-1. So k is the index for individuals in generation n-1. Then the population size of generation n, that is xn, is y1 plus y2 plus and so on plus yx n-1. So this is the number of descendants produced from individual 1 in the previous generation, and this is the number of descendants produced from the second individual in the previous generation, and so on. So if we add all these descendants, we get the population size of generation n. Now, each of these yks, so y1, y2, and so on, these are the number of descendants produced by a single individual. Therefore, we can calculate the expectation value of this s to the power of yk as this. So this is the probability that the number of descendants from the kth individual is equal to j, which is pj because it's the number of descendants from a single individual, right? So this expectation value is equal to this generating function, g of s. Now, let's try to calculate the generating function gn of s. So this is the definition. And using the partition theorem, we can split this probability into the sum. So we just rearrange the order of the summations. And here's the probability that the population size of the previous generation is equal to r. And given that condition, here's the conditional probability, right? So looking at this part, this is the expectation value. It's a conditional expectation value of s to the power of xn. So m is the number of individuals in generation n, so it's xn. And given that there are r individuals in the previous generation, then xn can be expressed as the sum of y1, y2, and so on, up to yr. Then we can split this exponential into the product. So this s to the power of y1 plus y2 plus and so on can be split into s to the power of y1 times s to the power of y2 times and so on. And since y1, y2, and so on, they are all independently and identically distributed, we can split this into the product of expectation values. And all of these expectation values have the same functional form because they are identically distributed. But we know that this is equal to g of s. So there are r terms, r factors in this. So we have g of s to the power of r. But now look at this entire thing. So this is the probability that the number of individuals in generation n-1 is equal to r times something to the power of r. So this is the same form as the generating function. Instead of having s here, we have g of s. So this is the generating function gn-1 with the variable of g of s. So it's not s, but g of s, because we have g of s here, we have g of s here. That means the generating function for generation n can be expressed as the function composition of g and gn-1. Since we are assuming that we already know the function gn-1, in principle, we now know the function gn. So we define the function gn, the generating function gn, in inductive manner. So g1 was just g of s, and g2 is just g composed g after g, that is g of s, and g3 would be g after g after g, that is g of s, and so on. So in general, gn becomes g after g after g, so we repeat applying the function gn times. So we have this. So starting from g1, we can calculate gn by repeatedly applying the same function g over and over again. And since g of 1 is equal to 1, as we have derived before, so if we put g1 equal to 1, then this is 1, and this is 1, so g2 of 1 is g of 1, and g3 of 1 is equal to g of 1, which is 1, so g of 1, which is g of 1. So for any n, gn of 1 becomes 1. Now that we have the generating function, we can calculate the mean mu n of xn from this formula. For n equal to 1, in generation 1, mu1 is just this, g1 prime of 1, but g1 is just g, so we have g prime of 1. Of course, g prime is the first derivative of the function g. And for n greater than or equal to 2, we have this recurrence formula, right? So gn can be expressed in terms of the function composition between gn-1 and g. So by using the chain rule, we can differentiate this function like this. So the derivative of gn with respect to s is equal to gn-1 prime of g of s times g prime of s. And we set s equal to 1, so we have this. So this is mu n minus 1, so it's the mean population size of generation n-1 times this is the population size of generation 1, so mu1. So if we continue this over and over, eventually we get mu n equal to mu1 to the power of n. So we can see the average population size makes a geometric sequence where the multiplication factor is mu1, the average population size or average number of descendants per individual. Next, we want to find the variance sigma n squared of generation n. And to do that, we differentiate the generating function twice. Okay, the first derivative was this. So by the chain rule, we have this. And if we differentiate this again with respect to s, we have this. So we differentiate this part and this part. So it's the product rule. And chain rule combined, we have this. So the second derivative of gn minus 1 of g of s times the first derivative of g squared. So this comes from this part. And then we have this first derivative of gn minus 1 times the second derivative of g of s. And to find the variance, we set s equal to 1. So we have this. And this part is g prime of 1 is the mean of generation 1. So that's mu1 squared. And this first derivative, gn minus 1 prime, is, as we have found out before, this is mu1 to the power of n minus 1. And this g double prime of 1, we can express this in terms of the variance of the first generation and the mean of the first generation, like this. We know the values of mu1 and sigma1, so that's okay. But we do not know the values of these things. So gn double prime and gn minus 1 double prime. So first we need to find out what these values are. So to simplify the notation, let's say un is equal to gn double prime of 1. So substituting this, we have this difference equation for un. So we have un here. So putting this to the left-hand side, we have mu1 squared un minus 1. And this one is just this term. Now, let's solve this difference equation. Let's name it star. And we separate two cases. When mu1 is not equal to 1 and when mu1 is equal to 1. We need to deal with them separately. So, first case, when mu1 is not equal to 1. We first solve the homogeneous difference equation. So putting this right-hand side equal to 0, we have this homogeneous equation. But this is very easy to solve because we can see that un is just a multiple of un minus 1 and the scaling factor is mu1 squared. So the general term for un becomes this. So b, some constant, times the scaling factor to the power of n. Scaling factor is mu1 squared, so we have mu1 to the power of 2n. And next, we want to find a particular solution for this inhomogeneous difference equation. And for that, we use the method of variation of parameters, just as we do for linear ordinary differential equations. So for that, consider this constant as a variable. So un is equal to some unknown sequence bn times mu1 to the power of 2n. And substitute this into this difference equation. And we get this. So the left-hand side becomes this. So we just substitute this into here and here. And by factorizing, so this mu1 squared cancels this negative 1 part. So we have the common factor, mu1 to the power of 2n. So we factorize this, and this is the left-hand side, which should be equal to this right-hand side. So by rearranging, we have bn minus 1 equals to this term. So sigma 1 squared plus mu1 squared minus mu1. So that's this part. So, and we cancel these, and we have mu1 to the power of n plus 1 in the denominator. And by looking at this form, it's reasonable to assume that Bn has this form. Okay, so some constant c, divided by mu1 to the power of n plus 1. So if we substitute this into this left-hand side, we have this. So bn becomes c over this thing, and bn minus 1 becomes c over mu1 to the power of n. Okay. So by simplifying this a little bit, we have this. And this should be equal to this. So we have this equal to this. So the constant c should be equal to this. So putting this constant c into this form, we have the particular solution as this. So un is equal to bn times mu1 to the power of 2n. And substituting the constants, we have this equation, and which can be simplified because we can cancel this n with this one of these n's. So we have this. And the general solution becomes the solution for the homogeneous case and the particular solution for the inhomogeneous case. So this way of solving the difference equation is exactly the same as the method for solving differential equations. And to determine this parameter, we can again use the same method as differential equation. That is, we use the initial condition. So when n is equal to 1, we have this. So u1 by definition is g double prime of 1, which is equal to this. So sigma 1 squared is known and mu1 is known. So this is a known quantity. And that should be equal to this. This n becomes 1. This n becomes 1. So we have this. So from this, for this is equal to this. From this, we can determine the value of b as this. So by combining all this, substituting this b into here, we have un equals to this expression. So the variance sigma n squared is gn double prime of 1. So this one is u, and minus mu n squared plus mu n. So everything combined, we finally obtain this formula for sigma n squared when mu1 is not equal to 1. And next we consider the case when mu1 is equal to 1. In that case, the difference equation becomes this. So un minus un minus 1 is equal to a constant, sigma 1 squared. So it's easy to solve this because it's an arithmetic sequence. So the general form of un is n times sigma 1 squared plus some constant. But we know that u1, so when n is equal to 1, u1 is equal to sigma 1 squared. So this constant a should be 0. Therefore, in general, sigma n squared is equal to this, equal to n times sigma 1 squared. So let's summarize the results we have obtained so far. For the mean, we have this. So for the mean population size of generation n is equal to the mean population size of generation 1 to the power of n. And for the variance, we have this. We have two separate cases when mu1 is equal to 1. So the average number of descendants per individual is equal to 1. Then the variance of the population size in generation n is n times sigma 1 squared. And when mu1 is not equal to 1, we have this a little bit complicated expression. This looks a little bit complicated, but we may simplify this expression or even unify them in one expression. So let's consider that. Simplifying, unifying, and understanding the variance. So we have these two separate cases, but we can actually unify them. First, consider this part. Okay, this is actually equal to this sum. Do you see? This is the sum of a geometric sequence. So 1 plus mu1 plus mu1 squared plus and so on up to mu1 to the power of n minus 1, which is equal to this. That is this part. Okay? So when mu1 is not equal to 1, sigma n squared can be expressed as this. So this factor times this sum. Now, if mu1 is equal to 1, then of course mu n is equal to mu1 to the power of n is equal to 1 for all n. Okay? So sigma n to the power of squared is equal to n times sigma 1 squared, but this n can be split into 1 times 1 plus 1 plus 1 plus 1 plus 1 and so on. So we add 1 n times. Okay? So this one may be expressed as this. So mu1 to the power of n minus 1, which is just 1, right? So this one can be expressed as this sum. So mu1 to the power of m, but this mu1 is 1, so this is just 1. But anyway, formally we can write this like this. So it's the same expression here and here. So whether mu1 is equal to 1 or not, we have actually the same expression for the variance. So here's the unified expression. This holds whether mu1 is equal to 1 or not. But remember, mu n is equal to mu1 to the power of n. So we replace these with this. So sigma n squared is equal to sigma 1 squared times the average population size of the previous generation times the sum of all average population sizes up to the previous generation. So that's an interpretation of the variance for generation n. That is, the variance of generation n is determined by the variance of the number of descendants per individual and the mean population sizes up to the previous generation. Alright, we now turn to the probability of extinction. Here, extinction means the population size becoming 0. Now, from the generating function, we can see that gn of 0 corresponds to the probability of extinction. Because if we put s equal to 0, all the terms will disappear except when j is equal to 0. That's this. Note that 0 to the power of 0 is 1. Okay? That's why this term remains. And recall the definition of g of s as this. And here we assume the value of s is between 0 and 1. Okay? We note the following properties of this function g of s. First, g of 1 is equal to 1. So if we draw the graph of t equal to g of s, then this graph always passes through this point, 1 and 1. And second, g of s is always positive if p0 is positive. If it's not 0. And third, g prime of s, the first derivative of g, is equal to this, which is greater than or equal to 0. That means g of s is non-decreasing function. Okay. And lastly, g double prime of s is equal to this, which is greater than or equal to 0. That means the function g of s is a convex function. So Summarizing all these properties, the graph of G would look like this. So S-axis and T-axis. Let's see. So this is 1 and this is 1. So it passes through this point, and it's always non-decreasing, and it's always convex. So it looks like this. Okay, exact shape will vary depending on the values of PJs, but in general, it looks like this. Before explaining how to find the probability of extinction, we need this lemma. So let f be a function twice differentiable and continuous, defined on the interval between 0 and 1, with its second derivative greater than or equal to 0 for all x in the interval. For any x1 and x2 with x1 less than x2, we have this inequality. So this ratio is greater than or equal to the first derivative evaluated at x1. So to prove this, we use the mean value theorem. According to the mean value theorem, there exists some x3 between this x1 and x2. It's an open interval such that this ratio is equal to this first differential coefficient at x3. Then again, applying the mean value theorem, we have this ratio equal to the second derivative evaluated at some x4 between x1 and x3. But by assumption, this is positive or 0. So this whole thing is positive or 0, but x3 is greater than x1. So that means this numerator is greater than 0 or 0 equal to 0. Therefore, we have the first derivative at x3 is greater than or equal to the first derivative at x1. So this is greater than or equal to f prime of x1. Therefore, we have this inequality, and we are done. Now, to find the probability of extinction, we again derive a recurrence formula for that probability. Let Gn be Gn of 0, which is the probability of extinction for generation n. We start from generation 0. So G0 is equal to G0 of 0, which is 0, because there is a single individual almost surely for generation 0. And for generation n, Gn is equal to Gn of 0, which is equal to this. So this is the recurrence formula we have derived before. So it's a composition G of Gn minus 1 of 0. So this one is, by definition, Gn minus 1. So from this recurrence formula, we can find G1, G2, G3, and so on in turn. For example, to find G1, we just plug in G0 to the function G, which is G of 0, which is actually P0. And to find G2, we plug in the value of G1 to the function G, which is G of P0, and so on. And for G3, we plug in the value of G2 to G, and so on and so on. Now, we prove that this sequence of Gn is a monotone, non-decreasing sequence. Okay, let's prove this. First, we have G1 equals to G of G0, and G0 is 0, so we have this, but this is just plug in the definition of G, then we find that this is just P0, which is greater than or equal to 0. But 0 is equal to G0, so G1 is greater than or equal to G0. So here we are actually using mathematical induction. So here's our premise. Suppose Gn is greater than Gn minus 1. And we know that G double prime of S is greater than 0 for all S in this interval between 0 and 1. So by the above lemma we have just proved this ratio, so G of Gn minus G of Gn minus 1 and Gn minus Gn minus 1, which is this. So according to the recurrence formula for Gn's, we have this here in the numerator. This is greater than or equal to G prime of Gn minus 1, so this value, right? But this is greater than or equal to 0, according to the properties of this function g. And by assumption, Gn is greater than Gn minus 1. So this denominator is positive. Therefore, this numerator should be non-negative, and we have this. And if Gn is equal to Gn minus 1, then we have Gn plus 1 equals to G of Gn, but Gn is equal to Gn minus 1, so we have this, but this is equal to Gn. So Gn plus 1 is equal to Gn. So since this equality holds, after above this n, Gm is equal to Gn, which is equal to Gn minus 1 for all m greater than or equal to n. So either case, we have Gn plus 1 greater than or equal to Gn. So this sequence Gn is monotone, non-decreasing. Now, as a corollary, we can say that Gn, the sequence, converges in this interval. So the proof is easy. This sequence is bounded between 0 and 1, and it's monotone, non-decreasing. So by the monotone conversion theorem you have learned in calculus, this sequence converges. So let this conversed value be g. So the limit of the sequence is defined to be g. And since we have this recurrence formula, we should have, at the convergence, g is equal to g of g. That means this g, this limit, is the fixed point of this function g, capital G. So by solving this equation, we can find the probability of eventual extinction. And we can solve this equation by repeatedly applying this recurrence formula. So we start from G0 and we find G1. Then we can find G2, G3, and so on. And this sequence is guaranteed to converge to some value. And the converged value is this G. So we know G0 is 0 and G1 is P0. Applying this formula, we find this is P0. And first consider the case when this P0 is 0. Then that means G is equal to 0 because G1 is equal to 0, which is equal to G0. And according to the proof we have just provided, if the consecutive terms in this sequence are equal, then all the terms after that are also equal to that value. So that will be all 0. So G0 equal to 0, so G is equal to 0. That is the fixed point of this function G. That means the population never goes extinct. So the extinction probability is 0. That is obvious because if all individuals produce some descendants, the population can never go extinct. And next, consider the case when P0 is greater than 0. First, we note that g of 1 is equal to 1 because the probability measure should be normalized. Therefore, g equals to 1 is always a fixed point. So if we plug in 1 to this function g, we always get 1. So 1 is a fixed point. But that does not imply that the probability of extinction is 1, because this fixed point may not be reachable from this initial condition. So let's examine these cases. When g prime of 1 is greater than 1, then we have this probability of extinction to be less than 1. So we have a fixed point somewhere less than 1. And in the case when g prime of 1 is less than or equal to 1, then the probability of extinction is 1. So this 1 is indeed the only fixed point of the function g. Let's see this more graphically. Recall that the graph of this function g looks like this. So s and t, it looks like this. So let's examine this more carefully. So when g prime of 1 is greater than 1, then it looks like this. So p0 is the intercept, and it's something like this. And if we draw the line, that is t equal to s, so it's a diagonal line. So this is 1, and this is 1. And so g prime of 1 means the gradient of this curve at this point, right? So this, if this gradient is greater than 1, then there is an intersection between this straight line and this curve. So this curve is t equals to g of s. Okay, so this is the fixed point, and this should be the probability of extinction. To see that, let's start from s equal to 0, because g of g0 is equal to 0. So we start from here. Okay, let's change the color. Then using this value, try to find this intersection with the straight line. And that is, so this is P0, and this is P0, because this line is t equal to s. So now we use this value to find the next value, that is this one. Then we find the next value on the line, and next value on the curve, next value on the line, next value on the curve, and so on. So it will converge to this value. So although this is a fixed point, so 1, 1 is a fixed point, but it's not reachable starting from this initial condition. Okay, so we start from here, 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 here. So it converges here. So that's the fixed point. When g prime of 1 is greater than 1. And when g prime of 1 is less than or equal to 1, then the curve should look like this. So let's first draw the straight line, t equals to s. And the curve is something like this. So s equal to 1 is here, and t equal to 1 is here. The curve looks like maybe like this. You know, the curve is always convex, so it will not go like this. It's always like this, going up, and it's convex. So if we start from here, then the next value is here, the next value is here, next value is here, and it converges to this point, 1, 1. So this point is the only intersection between this curve, and this curve is t equals to g of s, and this line, and that's the only fixed point of the function g. So that means, so if g prime of 1 is less than or equal to 1, this is the the limit of this sequence. By the way, this g prime of 1 is equal to mu 1. So mu 1. That is the mean number of descendants per individual. So if that's less than or equal to 1, then the population will go extinct eventually. On the other hand, when the mean number of descendants per individual is greater than 1, then the probability of extinction is less than 1. It may not be 0, but less than 1. Okay, that's all for this video. If you like this video, please hit the like button and please subscribe to this channel. See you later. Bye.